In this lesson, we will consider the factors which reduce the effectiveness of the transmission of radio waves, the various paths along which radio waves travel from the transmitter to the receiver, called propagation paths, and the different frequency bands and their uses. First of all, let us consider the factors which affect the propagation of radio waves. These factors fall into two categories, namely attenuation, which is the weakening of the wave, and refraction, which is the bending of the wave. Attenuation occurs in several ways. As the wave travels further away from the transmitter, it simply becomes weaker, like the waves in a pond emanating from where a stone is thrown. As range increases, the field strength of the wave decreases. It can be shown that this attenuation is proportional to the inverse square of the range. This means that if the range of the transmitter is to be doubled, the power required must be quadrupled. Surface attenuation occurs when a wave travels over the Earth's surface. Its strength will be attenuated by contact with the Earth's surface, because the wave induces a voltage in the Earth which takes energy away from the wave as it moves away from the transmitter. To reduce this attenuation, vertically polarized electric fields are used, which merely dip into and out of the Earth's surface, whereas a horizontally polarized field is in constant contact with the surface of the Earth, and the wave is completely attenuated within a short distance. The nature of the surface of the Earth over which the wave travels is also a factor in attenuation. Radio waves attenuate more over land than over the sea. Mountains, forests and deserts cause the greatest attenuation of radio waves. Surface attenuation increases as the frequency of the signal increases, and so frequencies above 2 MHz are of little use for long-distance transmissions. Ionospheric attenuation occurs when radio waves penetrate the ionosphere, which is suffused with free electrons. As radio signals propagate through the layers of the ionosphere, they begin to transfer energy to these electrons, setting them in motion. This results in the electrons vibrating, which can cause them to collide with other molecules, ions and electrons. Each collision dissipates a small amount of radio signal strength as energy is transferred from wave to particle, and the radio wave returning to Earth will have lost some of its strength. The frequency, and hence the wavelength of the radio wave, is important. The longer the wavelength, the greater the ionospheric attenuation. Note that this is the reverse of ground attenuation. Another type of signal weakening is atmospheric attenuation, or scatter. Because the atmosphere contains solid particles, such as water, pollutants, and ice, these will reflect and scatter radio waves of a sufficiently high frequency, those above 5 GHz. You will recall that the wavelength of radio waves in the 2 GHz bands, 3 to 300 GHz, ranges from 10 centimeters down to a millimeter. Water droplets have similar sizes, and that is why they reflect and scatter radio waves. Reflection of signals off buildings and hills, etc., will weaken any signal. Consequently, aerials should be positioned as high as possible or well clear of buildings and other causes of refraction. Static interference in the atmosphere also attenuates radio signals. It is caused by an imbalance of positive and negative electrical charges in atoms which come into contact with each other, causing electrons to be transferred from one atom to another. Rain and thunderstorms and solar activity are the frequent cause of static interference, and it is worse at lower frequencies. If there is much static interference, the strength of the signal may have to be increased. The strength of the signal compared to the amount of interference, measured in decibels, is known as the signal-to-noise ratio. If internal noise in a receiver can be reduced, then the receiver will be able to process weaker signals, thereby increasing the effective range at which a usable signal can be received. However, this is an expensive business. The other category of factors in radio propagation is refraction, or bending of the waves. This can happen in several ways, and may be a hindrance, or it may be a help to radio wave propagation. If radio waves or light waves pass through one medium and then through another, they will bend or refract because of a change in velocity, such as light through a prism. This graphic shows a straw which has not yet been inserted into clear water. Now, when it is inserted into the water, it appears to bend. This is because the light waves travel in water at 75% of the speed that they do in air. The same occurs to radio waves in the ionosphere, as they pass into a more densely ionized, that is, negatively charged, layer. This ionospheric refraction is very useful, as it causes the radio wave to bend back towards Earth. Refraction decreases as the frequency of the radio signal increases. We will look at this in more detail shortly. Equally useful is atmospheric diffraction. In the low and medium frequency bands, radio waves tend to refract or bend to such an extent that they remain in contact with the Earth's surface, which increases range, possibly to thousands of kilometers. This bending also occurs in the VHF band during some meteorological conditions, which results in a radio wave hugging the Earth and increasing range. This effect is known as super-refraction. The necessary conditions are a decrease in relative humidity with height, temperature falling more slowly than standard, and a high pressure system, typically where warm air flows over cooler surfaces. Sub-refraction occurs in conditions of increased relative humidity, lower than isotemperature and low pressure, typically where cold air flows over a hot surface. It results in reduced range. However, not all refraction is beneficial. Coastal refraction occurs because a radio wave travels faster over the sea than it does over land. As a result, any wave that crosses a coastline at other than 90 degrees will bend slightly towards the medium in which it travels slower, namely the landmass. Again, the degree of refraction decreases as the frequency of the radio signal increases. Now let us look at the ways in which radio waves are propagated. There are three ways in which electromagnetic energy travels from a transmitter antenna to a receiver antenna. Two of them, surface waves and space waves, do not reach the ionosphere, and collectively they are called non-ionospheric.